Prior to the 1900s, we seemingly had a perfectly good understanding of the laws governing the physical universe handed down to us by the great Isaac Newton. These are the laws we still teach high school kids around the world, the laws of so-called classical physics. And for those of you who like math, here are some of the essential equations, but those are details. At the core of Newton's perspective is the idea that if you specify how the world is right now, the positions and velocities of all ingredients, and you specify the forces acting on those ingredients, the laws predict how the world will be at any subsequent moment. The framework, it's sleek, it's elegant, it's powerful, and it's rigid in its determination of the future. And it worked. The predictions about the future, where a pendulum would be as it swung, where a ball would land when thrown, where the moon would be in its orbit around the Earth. All of these predictions and every other that was made, all of them were spot on accurate. That is, until the early years of the 20th century, when scientists gained the capacity to explore the micro world, the world of molecules, of atoms and subatomic particles, because in this realm, the predictions from Newton's math were wrong. The data revealed that new rules were needed to understand the microscopic realm, and remarkably, within just a few decades, a generation of scientists, including the likes of Albert Einstein, Max Planck, Niels Bohr, Werner Heisenberg, Erwin Schrödinger, Max Born, and many others. This group of brilliant thinkers ushered in a new understanding called quantum mechanics. Now, quantum mechanics, it comes with its own powerful mathematical formulation. But again, one can grasp the central new idea of quantum mechanics even without the math. Whereas Newton said, "Tell me how the world is now, and I will tell you how the world will be tomorrow," quantum mechanics says, "Tell me how the world is now, and I'll tell you the probability that the world will be one way or the other tomorrow." And according to quantum mechanics, these probabilities provide the deepest and most precise description of the physical unfolding. Gone, completely gone, according to quantum mechanics, was the rigid certainty of the classical world. Now, much has been made of Einstein's resistance to the probabilistic nature of quantum mechanics, the famous and frequently quoted, "God does not play dice." But Einstein did not deny that quantum probabilities provided a spectacularly accurate description of the microscopic realm. Instead, he firmly believed that quantum mechanics was only a provisional theory, one that would ultimately be replaced by a deeper understanding that would not rely on probabilities. And toward this end, Einstein, he worked tirelessly to expose qualities of quantum mechanics that he hoped would be so obviously unacceptable, so counter to any reasonable person's expectation of how the world works, that everyone would have to agree with his view that quantum mechanics was not the final story. And in 1935, with two colleagues, Boris Podolsky and Nathan Rosen, Einstein believed he had finally found the ultimate quantum mechanical Achilles heel with a property inherent to quantum mechanics called quantum entanglement. Briefly put, Einstein and his colleagues found that, according to the math of quantum mechanics, if two objects interact and then widely separate, a subsequent measurement on one of those objects, revealing one or another quality, would have an instantaneous influence on the other object regardless of the distance between them. Einstein called this strange quantum connection, he called it spooky. Spooky action at a distance, and it troubled him deeply. His straightforward, intuitive belief was that widely separated objects are independent of one another. But quantum entanglement seemingly denied that by providing an invisible quantum connection capable of linking the distant objects together, or, as the name says, entangling them. Einstein could not accept this quantum view of reality, and so he concluded that something had to give. Quantum mechanics could not be the full and final story. That's the upshot of the 1935 so-called EPR paper. Now, for years, no one paid much attention to the EPR result, mostly because quantum mechanics worked. And moreover, no one could see a way to test Einstein's speculation that quantum mechanics would one day be replaced by a deeper understanding that would not need probabilities. That is, until 1964, when a physicist named John Stuart Bell proved mathematically that there was a way to test Einstein's more conventional view of reality. That is, to test his view that particles always have definite features and there's no spooky connections, no quantum entanglement. And this year's Nobel Prize in Physics has been awarded to Alana Spey, John Clauser, and Anton Zeilinger, whose collective works have carried out that test, establishing to most people's satisfaction that Einstein's conventional view of reality is ruled out, that quantum entanglement is real, and more than that, have shown that quantum mechanics and entanglement can be leveraged for applications ranging from quantum computing to quantum teleportation. Spectacular results that have both changed our view of reality and whose technological implications are both exciting and profound.